In this lecture here, we want to start talking now about solving linear inequalities and absolute value inequalities. So you're going to be given some equation that's going to have some type of inequality. It could be a strict inequality or just a regular inequality. And what I want to do is I want to show you how you're going to show the solutions for it and how you use some of the tricks to solve some of the problems. Okay, so what we're going to work through in this lecture, we're going to talk about interval notation first, then we're going to solve linear inequalities, then we're going to recognize inequalities with no solutions or have all real solutions, and I'll do an example of at least one of those and I'll talk about the other one. And then I want to talk about how you solve compound inequalities, and then finally how you solve absolute value inequalities. Okay, so solving inequalities is the process of finding the set of numbers. So here's the thing. You're going to notice when we solve these inequalities, the solutions are going to be a set. Okay, so there's going to be more than a single solution. So actually, there's going to be an infinite number of solutions to a lot of these, and we have to figure out, how to show that. Okay, so these numbers that we find this set are called the solutions of the inequality, and we say that they satisfy the inequality. Okay, so the set of all solutions is called the solution set of the inequality. So what our goal here is in this lecture is how to find the solution set. Okay. So one way we're going to show the solution set is with interval notation. So let's work through, how we show things with an interval notation, and then you'll see the corresponding set builder notation. And then I'll also, when we get to a solutions, talk about how you show things on a number line. All right, so the open interval. So notice how we have these parentheses here. Parentheses a comma b represents the set of real numbers, but this is important, but not including a and b. So whenever you see this open parentheses here, okay, like this, all right, that just means it's all x such that x is in between a and b, but not including a and b, okay? Okay, so it literally starts right up after a and goes right up until right before b. So then this other thing that's a little different is this closed interval, and it's got these brackets that look like this, okay? The closed interval represents the set of real numbers between and including a and b. So whenever you see something like this with these brackets here, it's all x such that x is between and including a and b. So a is less than or equal to x, less than or equal to b. So including a and b. All right. The infinite interval a comma and what you see here, this sign right here, this means infinity. A to infinity. All right, this represents a set of real numbers that are greater than a. So whenever you see open interval to a comma to infinity, this is all x such that x is greater than a. If you were to write it like this, let me just do, you can have this bracket here, all right, be the closed bracket. This is all x such that x is greater than or equal to a. That's okay too. All right, the interval negative infinity to b, and you can see the closed bracket here for this one, represents the set of real numbers that are less than or equal to b. Okay, but you notice here that whenever you see an infinity sign or a negative infinity sign, it's always the open bracket, never these closed brackets here. It's always the open bracer, never the closed bracket around infinity. That's because parentheses indicate endpoints that are not included in an interval. So square brackets indicate endpoints that are included in an interval. Parentheses are always used when you see infinity or negative infinity, okay? The reason being is like infinity is not really a number, right? This is just a concept. This means increasing without bound. It goes on forever. It goes down to negative numbers forever. Okay. So what we want to do now is talk about how you're going to solve linear inequalities. Okay, so a linear inequality in x can be written in one of the following forms here. Okay, so it's just ax plus b is less than 0, ax plus b is less than or equal to 0, ax plus b is greater than 0, or ax plus b is greater than or equal to 0. All right, so you're going to solve this. Okay, solve as you would a linear equation. But the only thing you have to remember, and I'll do an example of this, is when you multiply or divide both sides of an inequality by a negative number, okay, the direction of the inequality sign is reversed, or you'll hear me say it's flipped. Okay, you flip it. Right? Like for example, if you see something like this, minus 2x is less than 10. When you go to solve this and divide by a negative number here, those cancel out. Well, I divided by a negative, so this needs to flip, and x is going to be then greater than 10 divided by negative 2 is negative 5. So that's the only thing you have to remember when you go to solve inequalities here. All the other rules are exactly the same. Like if you just have 2x is less than 10, if you divided by a positive number here, you would not flip the inequality. So it's only when you multiply or divide both sides by a negative number do you flip the inequality. All right, so let's do this one. So I actually have this one worked out here, just so you can see. So I want to solve and graph the solution set on a number line, okay? So you have 2 minus 3x is less than or equal to 5. Okay, so you're going to solve as you would a normal linear equation. So you're going to subtract 2 from each side. These are gone, so 5 minus 2 gets you this 3. And then look, when you go to divide by a negative number, okay, I'm dividing by a negative number, you need to flip. So notice how it's a less than or equal to, and now it's a greater than or equal to. You flip it. All right? These negative 3's cancel. Whoosh, whoosh. And 3 divided by negative 3 is negative 1. So because you flip the inequality, the solution is x is greater than or equal to negative 1. All right, so this is how you would show that in set builder notation. All right, x such that x is greater than or equal to 1. The interval notation, because it has an equal sign here, gets the closed bracket. You would start at negative 1, comma, and then it's everything above that. So you would go to infinity. On a number line here, you would put like the number line, and then you're just going to highlight or shade in. You're going to say, okay, it can be negative 1. So I'm going to close bracket, and then I'm going to highlight in on the number line all the way to the right, because it's all the numbers that are greater than or equal to negative 1. All right, let's try this one. Okay, and I'm going to go back and I'm going to do the same thing. I'm going to show you set builder notation, interval notation, and then the solution on a number line so you can see it all. Let's try this one. Let's look at 2x plus 5 is, let's actually just do greater than 10. So look, you're going to subtract 5. Boom. Okay, so this becomes 2x is greater than 10 minus 5 is 5. You're going to divide by 2. And you're going to get x is greater than 5 halves. Okay, which is 2.5. But the way you would show this solution, okay, in set builder notation, it would be x such that x is greater than 5 halves. An interval. Okay. Well, look, it's a strict inequality, so you would go, it's all numbers that go from 5 half to infinity. And then on a number line, you'd sketch the number line. All right, so 5 halves, well, 5 divided by 2 is 2.5. So at 2.5, you'd put this type of bracket here, okay, because it starts right after 5 halves. And then you would shade everything to the right and say, okay, it's all numbers that go that way. All right, so look, hopefully you see that this is really just straightforward solving a linear equation. Just remember, when you multiply or divide by a negative, you gotta flip the inequality. Otherwise, then you just got to show your solution as either set builder, interval, or on a number line. But the steps that we've used to solve are ones we've all used before. All right, let's try this one now. Okay. All right, so this one is an example of recognizing inequalities with no solutions or all real numbers as solutions. So, all right, you're going to go, okay, let me distribute here. So this is 3x plus 3 is greater than 3x plus 2. Well, look, notice what happens after you subtract 3x. Do you notice how you're just left with 3 greater than 2? All right, this is a true statement, right? 3 is greater than 2. So what that means is, look, the x's don't matter here. All right, the solution here, whenever you just end up with a true statement like this, all right, the solution is all real numbers. So it would go from negative infinity to infinity, right? If you ever get a problem with something like this, so what if you instead got 2 is greater than 3? Okay, that's a false statement. Okay, that's just not true, right? And so what that means is there's no solutions. Or the inequality you have, if it boils down to something like this, means there's no solution. And that's okay. You know, sometimes that'll happen. So this is a case here where the solution would be all real numbers. And then if you got a false statement like 2 is greater than 3, that would indicate that there's no solution to the inequality. All right, so now let's talk about compound inequalities. So look at this one. I said, look, I want you to solve this. I want you to solve 1 is less than or equal to 2x plus 3, which is less than 11. So when you go to solve a compound inequality, all right, you want to isolate the x by itself. So you're going to subtract 3. But what you have to do in these cases is subtract it also away from both sides here. So that's gone. So 1 minus 3 is minus 2, is less than, I'm left with 2x. And 11 minus 3 is less than or equal to x, is less than 8. So now I'm dividing by 2, not dividing by negative numbers, so those cancel. So I'm left with negative 1 less than or equal to x less than 4. So look, here's how you would show this. Look, set builder notation. It's x such that negative 1 is less than or equal to x less than 4. In interval, well, you're going to negative 1, but it's a less than or equal to, so it's going to be a closed negative 1 to 4. It's a strict inequality, so it's going to be an open bracket. So then on a number line, so look, you're going to go to negative 1, you're going to put the closed bracket. Then you're going to go to 4, you're going to put the open bracket. And then it's just shade in between along the number line. Say, okay, it's all numbers starting at negative 1 and going up to 4, but not including 4. All right, let's try this one now, okay? So let's just solve and graph the solution set again, so I'll do the same thing. So you're going to start by subtracting 2 from all sides. So minus 4 minus 2 gets me negative 6 is less than or equal to minus 3x. These cancel, and then 8 minus 2 gets me less than 6. But now look, when I divide by negative 3, what is going to happen to the inequalities? They're going to flip. Okay, so minus 6 divided by minus 3 gets me 2. This flips, is greater than or equal to, these cancel, x. And this, because I'm dividing by negative, flips. And 6 divided by negative 3 is negative 2. Notice how this is weird, so I'm just going to rewrite it. It's negative 2 is less than, so because you're going to have the mouth of the inequality open up towards the same value, is less than or equal to 2. So set builder, you're going to show the solutions. It can be, x such that minus 2 is less than x, which is less than or equal to 2. You can show it as minus 2 to 2 and then close bracket there. And then on a number line, open bracket at negative 2, close bracket at 2. And then right there. There's all the values that it could be. It could be anything in between those two. All right, so last thing I want to talk about is solving absolute value inequalities. So if u is an algebraic expression and c is some positive number, okay, you have two cases, right? The solutions of the absolute value of u is less than c are the numbers that satisfy this equation right here. So minus c is less than u, less than c here. So you're going to solve with a compound inequality. While this one here, the solutions of the absolute value of u is greater than c are the numbers that satisfy these two equations separately. So it's u is less than minus c, or u is greater than c. Okay. So these rules are still hold if you replace these strict inequalities with less than and equal to or greater than equal to. It doesn't matter. All right. So let me do two different solutions here, two different examples, so you can see here. All right, so let's try this one. Solve and graph the solution set on a number line for 18 is less than the absolute value of 6 minus 3x. So I'm going to rewrite this, okay? So I'm going to rewrite this as the absolute value of 6 minus 3x is greater than 18. So look, going back, greater than, right here, okay? Notice how I have it written as a greater than. I just turned this around so I could use the rules. So I have to break this up into two equations, okay? So the first one is that u, what's inside here, is less than negative c. So it's this is less than negative c. So in this case, it's negative 18. Or another solution is that, in this case, the algebraic expression u is greater than c. So in this case, it's just greater than 18 there. All right, so let's solve, right? So let's subtract 6. So these are gone, so I get minus 3x is less than, in this case, minus 24. Now be careful here. I'm going to divide by negative 3. What happens when you divide by a negative? Flips. So x, negative divided by a negative, x has to be greater than 8. Or in this case, you're going, in this case, greater than 12. Divide by negative 3. So x is less than, because you flip, you divide by a negative. 12 divided by negative 3 is negative 4. All right, so the way you would show this, I'm going to show you how to show this in interval. So it's all numbers less than negative 4. So it'd be everything from negative infinity to negative 4. And then using set notation, you'd union with all numbers greater than 8. So from 8 to infinity. And then on a number line, I'm just going to go by 2's. It'd be negative 4, everything this way, and then 8, and then everything this way. All right, let's do one last one. So I did a greater than. So let me do a less than. So let's look at the absolute value of 2x minus 4. And so it'll do a less than is less than 10. So look, when you have this less than, you just have to take your algebraic expression, and it has to be between 10 and negative 10. So then just solve this. So plus 4 to each side here. So minus 10 plus 4 is minus 6, less than 2x. Here, this is 14. And then I'm divided by a positive number, so I do not need to flip. So this is minus 3 is less than x, which is less than 7. So in interval notation, it's minus 3 to 7. And then on a number line, just going out here, well, here's minus 3, here's 7, open brackets, And then this is all the solutions here. All right, class. So I hope this helps seeing this. Just the big takeaways here. Sometimes you're gonna have to know, like, oh, I have to solve this absolute inequality. Let me remember these formulas, and then otherwise, just remember whenever you multiply or divide by a negative, you're gonna flip the inequality.